let's continue. So in the previous slide, we present the definition of Laplacian of a scalar, which is the Laplacian of a scalar equals to the divergence of the gradient of scalar 5, and also the definition of the Laplacian of a vector. So the Laplacian of vector A equals to the gradient of the divergence of A minus the curl of A. And before that, before we describe the definition for Laplacians, we stop at the two equations, equation 5.18 and equation 5.21. We see that the two equations, this equation is derived from what? Derived from Gauss's law of electrical field. And this equation is derived from Ampere's sequential law, the two Maxwell equation. And the derivation of the two equations, what is the significance of the two equations? In the two equations, we try to express the influence of source, electrical charge source, and electrical current source. J, electrical charge source low, in terms of what? In terms of electrical scalar potential phi and the magnetic vector potential A, right? So here we don't, in the two equations, you don't see electrical field intensity E or magnetic field intensity H. You see phi and A, the electrical scalar potential and magnetic vector potential. However, because in the same equation, what troubles us is in the same equation you have both phi and A in the same equation. So it becomes not that clear to reveal the relationship between electrical voltage source and electrical source and potential. It's not that easy to see the relationship between electrical current source and magnetic vector potential. Therefore, we introduce the two Laplacian operator. With the help of the definition of Laplacian operation, the two equation becomes equation 5.23a and 23b. Okay? So you should do the substitution yourself and try to come up with the two equations. So with the substitution of Laplacian of phi and Laplacian of A, we end up with the two equations, which still trouble us, right? Because in the two equations, you have phi, you have A, and they show up in the same equation. You have low, you have J, you have source. So what do we want? What do we want is, in the first equation, I want to get rid of A. In the second equation, I want to get rid of phi, so that to reveal the relationship between J and A and low and phi. Alright? So to do this, we need some extra help. Right? 这你的责任啊，从下面这两个式子到这两个式子，你自己把上面那个定义套进去带进去套一下哈，应该可以得到 5.232A 跟 B 这两个式子啊。但这两个式子比较令人讨厌的是，它们的 A 跟 phi 还是搅在一起 ，A 跟 phi 还是出现在同样的式子里头，所以我们要想办法把 A 跟 phi 把式子稍微清一下了啊，就是 希望 A 只跟 J 有关 ，phi 只跟 low 有关。那要怎么做？这边的话，我们要用所谓的 Lorentz condition， 右下方你看到 Lorentz condition， 还有呢 Helmholtz theorem，right？ 在这个 Lorentz condition 是建立在 Helmholtz theorem 之上的哈。Alright, so let's begin with the Helmholtz theorem. If there is a vector, we don't know the vector directly. However, you know the curl, say you have a vector F. We don't have the direct description of F. However, Helmholtz theorem tells you that if you know the divergence of F, and you also know the curl of F, which are the longitudinal derivative of F and lateral derivative. What is longitudinal derivative and lateral derivative? As I already mentioned on Tuesday. Lateral derivative is what? Is the spatial variation in the direction perpendicular to the vector. 跟一个向量正交的方向，也就是说，假如我的向量是这个手的那个箭头方向的话，往侧边的方向去观察，看它有没有变化，这个叫做 lateral derivative， 也就是 curl operation 告诉你的。好，所以 curl operation 的这一个空间微分给出来的是这一个向量的 lateral derivative。那 divergence operator 呢 ？divergence operator 我们称之为 longitudinal derivative， 也就是顺着这个向量的方向去做空间的微分。所以顺着这个向量的方向，假如它的向量的这个物理量的量子会变大、会变小、会变方向的话，那它的你就有所谓的不为零的 longitudinal derivative。所以 Helmholtz theorem 所要讲的事情是说，我们不用直接知道 F 这一个向量是什么东西，我们只要知道 F 的 divergence 跟 F 的 curl 这两个知道，我们就可以知道 F 是什么东东。好，那这边的话呢，我们是套到磁向量位能 A 上面。但我们有点把 Helmholtz theory 倒过来用OK。So from the beginning of this section of chapter 5, we say that B, the magnetic flux density, equals to what? Equals to the curl of A. The curl of the magnetic vector potential A, right? Do you know what is A? If you know B, can you derive A? Well, the answer is no. 所以我们知道 B 里面知道它所对应的 A， 不知道啊。不，因为说你知道 A 的话，你把它做 curl operation， 你就可以得到 B。但你知道 B 不一定能够得到 A， 不一定能够得到 A。So what are the consequences of Helmholtz theories? The Helmholtz, well, we only know that B is related to the curl of A, but we don't know what is the divergence of A. So in other words, you are at liberty of defining what is the divergence of A, and that is what we are going to do. To uncouple the equations, we make use of the Helmholtz theorem, which says that a vector field is completely specified by its curl and divergence. Then what I told you that if you know the divergence and curl of a vector, then you can fully describe the vector field. On the other hand, if you only know the curl of A, which is equals to B from our assumption at the very beginning, we are at the liberty to specify the divergence of A. Well, because so far it didn't tell you what the divergence A shall be. And based on this theory, we choose the divergence of A, that is, equals to the minus of Newton's element times the time derivative of phi, the electrical scalar potential. Then you are surprised, saying, well, can we do that? Well, there's no hurt for doing that. We have the ability to choose this. And so this condition is referred to as the Lorentz condition. 劳伦兹条件吧，好吧。当初第一个这样做的人也是蛮大胆的嘛，OK， 然后就直接把磁向量位能 A 跟电存量位能 phi 用这个关系把它连在一起你说可以这样干吗？你有人说不能这样干啊，好吧？那问题是这样干的好处很多，你等一下就会看到当你这样干的时候，会发现前面两个式子就可以大幅度的简化Suppose that the divergence of A can be expressed as the minus of mu times epsilon times the time derivative of phi. What it becomes to is our two equations. These are the two equations we begin with. So for the equation down below, because we define, we use the Lorentz condition. So directly, the things in the parentheses can be cancelled. Because we choose divergence of A happens to be the negative of mu times epsilon times the time derivative of phi. So this term can be eliminated because of the Lorentz condition. And the consequence of that is Laplacian of the magnetic vector potential A minus mu times epsilon times the second order time derivative of A equals to mu minus mu times J. So that's what we want. We directly relate the magnetic vector potential A with electrical current density J. And we only have A. And furthermore, what is the form of this equation? In this equation, you have what? You have second order spatial derivative. You have second order time derivative. So this is what? What is this second order partial differential equation? This is the so-called wave equation as we already seen in chapter 3. 我们在上学期的时候在做电磁波的推导的时候已经有看过了，这个就是什么？这个就是波动方程式。假如你的物理量 A 能够满足这一个关系式，也就是它的空间二次偏微分跟时间的二次偏微分能够满足这个波动方程式的话，能够符合这个二阶偏微分方程式的话，它就形成一个可以传播的波。这个我们在第3章的时候，我们有导出电场跟磁场的波动方程式的形式。那这边看到的是，即便我们这边不直接用电场跟磁场，用的是电向量位能跟磁向量位能跟电存量位能，你也可以导出波动方程式。Alright, so we can do this. We can also apply the Lorentz condition to the first equation, that is the Laplacian of phi, the electrical scalar potential phi, plus the time derivative of gradient of divergence of A, which you can replace divergence of A with this, and then you end up with this equation. It's also a second-order differential equation of both second-order spatial derivative and second-order time derivative. So the Laplacian of phi minus mu times epsilon times the second-order time derivative of phi equals to what? Equals to minus rho divided by epsilon. Alright? So here we successfully express the electrical charge source and the electrical current source, rho and phi and J, in terms of electrical scalar potential phi and the magnetic vector potential A, right? In the form of wave equation. So they are the differential equations related to electromagnetic potential phi and A to the source charge and source current, rho and J respectively. Right. So with the help of Lorentz condition and the introduction of electrical scalar potential and magnetic vector potential, we can successfully derive the relationship between charge source and current source with electrical scalar potential and magnetic vector potential. All right. So these two relationships are very helpful in treating practical problems. 也就是说，在实际的电磁运用问题的处理上，基本上我们都是不会直接用电场跟磁场去解，不会直接从电荷电流的时空分布来去直接解电场跟磁场，而是先利用电荷跟电流的时空分布，找出它所对应的电存量位能跟磁向量位能，然后把这个电存量位能跟磁向量位能做微分，做空间的微分。像是假如你能够解出 V， 也就是这边的 phi， 那多加一个归列的 operation 就是电场了。好，所以有 V 跟有 phi 跟 A 啦，有那个存量位能跟磁向量位能，其实离电场跟磁场就是多加一个微分而已。好，所以应该说，在实际的问题上面，直接从 low 跟 J 的去算 E 跟 H 是困难的，但是用它们去算 phi 跟 A 是没那么困难的，而用 phi 跟 A 来去算 E 跟 H 就简单了。好，这个在实际的应用问题上面，是如此处理的哈。那当然，我们时间的关系，目前可能对大家来讲还没办法去展示这样子的那个效果了哈。不过先有个印象，好不好？好。Before proceeding further, we shall show that the continuity equation, that is, the divergence of J equals to the minus of the time derivative of rho, is implied by the Lorentz condition. So I guess you may surprise that how comes that the Lorentz condition is valid, is legitimate, 合法的 legitimate. Well, even though we cannot prove it directly, we can according to some observation of the EM equation relationship, we are pretty confident about the validity of the Lorentz condition. Here's one example. The continuity equation is implied by the Lorentz condition. So here's the Lorentz condition, the divergence of rho equals to the minus of v times epsilon times the time derivative of phi. If you take in the Laplacian of the Lorentz condition on both sides, now that this is a scalar, this is a scalar, so you are free to apply Laplacian on the two sides of the equation, and you change the order. You change the order of operation of them, you end up with equation 5.27, right? And as I already mentioned on Tuesday, that because time and space are independent, so the time derivative and spatial derivative can be swapped. The order of the differentiation can be swapped. All right, so we first take in the Laplacian of Lorentz condition, we change the order of differential operation. Next, we substitute charge and potential, current and magnetic potential. And then we use the Lorentz condition again to get the so-called continuity equation. 好，基本上我觉得这有点掉到诡辩的那个状况底下了哈，不过没关系啊，反正课本都写了，我们就看一看了哈。那有点自设了一个假设，然后用在这个假设底下去证明这个假设哈。OK 好，所以当然还好，我们在工程里头不需要不需要像数学系一样那么严格的证明了哈。我们觉得看起来对就对了哈 ，OK 好，反正应用在工程上面是可以用的就 OK 哈。Alright, so we substitute the two wave function of electrical charge and electrical scalar potential, electrical current and magnetic vector potential into the Lorentz condition. So we end up with this equation. So by swapping by placing this term to the left and placing this term to the right, so you end up with two relationships. Here again, you can cancel this thing out based on the Lorentz condition. And because the left-hand side is 0, because of the Lorentz condition, the left-hand side is 0. How about the right-hand side? Right-hand side is mu times divergence of J plus the time derivative of rho. So the right-hand side is 0 as well. So as long as the Lorentz condition is satisfied, you are guaranteed to have the so-called continuity equation. Because if this thing equals to 0, what is this thing? Then the continuity equation says that the divergence of J equals to the minus of time derivative of rho. Okay, so here is a trick to show you that the Lorentz condition may be closely related to the continuity equation. All right. So again, as I already mentioned, the electrical scalar potential and the idea of potential is very useful in treating actual electromagnetic problems. We don't have to solve E and H field directly from electrical and current sources. We can simply solve them in terms of magnetic and electrical scalar, magnetic vector potential and electrical scalar potential, then perform differentiation to get the E and H field that we need. All right? Now, okay, so let's move on to section 5.2, which are potential function for steady field. So we will introduce the electrical scalar potential, which in other words is voltage. It's voltage. So we will examine the relationship between voltage and the electrical field intensity under the condition of steady field. And we can use the point charge source distribution to calculate the voltage distribution, voltage function due to point charge electrical field, so that we can find the potential distribution of a complicated charge distribution based on the superposition law, 叠加定理 superposition law. And once we have the voltage, once we have the electrical scalar potential, we can find the electrical field associated to it based on the gradient operator. As I already put it on the board, that electrical field intensity is directly related to the gradient of electrical potential under the condition of steady field. And by the end of this session, we'll look at the magnetic vector potential of a short current line. All right? So, to the left is the complete expression of electrical field intensity with electrical scalar potential and magnetic vector potential. However, under the condition of steady field, that is, we don't have time varying terms, the second term to the right can be eliminated. So you're left only with E equals to the minus of gradient of phi. The electrical field intensity is the minus of the gradient of phi, gradient of the electrical scalar potential. And what we learned in the previous section is that the the field. The electrical field intensity, which is expressed as the gradient of phi, is the direction of E. Is what? Is perpendicular to the phi function of equal magnitude, which means in this figure we have several planar surfaces. They are the so-called equal potential surfaces. 等电位面也是等电压面我们这样称之为等电位面。那么通过等电位面的是电场线 electrical field 而这个等电场线电场的向量跟等电位面有什么关系？因为电场的这个向量是等电位那个分布那个电位取归零之后得到的，所以它跟它正交所以你看到的电场跟等电位面的关系是什么？正交垂直所以电场线跟等电位面或者是说等电压面等电压线都是垂直的关系这个我们在各位以前在电力学的时候应该都已经很熟悉了嘛Alright, so for two equal potential surfaces, say phi A and phi B, the potential difference, that is phi A minus phi B, can be found by taking the line integral from B to A in terms of the summation of differences in phi. Okay, so what I'm just trying to express is this term. That is the line integral from point A to point B with respect to the small differences in phi. And the phi, that is the amount of change in phi, can be expressed in terms of the dot product of gradient of phi and the differential length dl, which is more easily to be carried out in calculus. 在积分的时候，后面那个式当然比较容易去操作嘛，你只要知道phi这个物理量的梯度然后你给定一个积分路径的话，就可以去把它算得出来那这两个式子是一样的虽然多了一个负号，但差别在于哪里？差别在于你的积分的起点跟终点有交换So equation 5.30 says that the differences between phi A and phi B can be expressed as the line integral from the negative of line integral from point A to B in terms of gradient of phi with a specified differential length. Alright, so for electrical field, we know that the gradient of phi can be replaced with this relationship. The electrical field intensity is the negative of the gradient of electrical scalar potential. So the differences in electrical potential is the line integral of electrical field intensity in the gradient from point A to point B. Okay? And we already done something like that in section 2.1 as we discussed the integral form of Maxwell equation. And so you can identify that the line integral of electrical field intensity from point A to point B is actually the voltage difference between point A and point B. So the potential difference in the static field case has the same meaning as the voltage. So that's already, as I already mentioned, under the condition of static field, the difference in electrical scalar potential is what? Is simply the voltage. So voltage is an imaginary physical quantity. It's not real. Voltage should be regarded as the line integral of electrical field intensity. electrical field intensity is real, voltage is not. However, voltage is easier to understand and easier to operate. So use voltage anyway. 所以虽然说电压并不是真实的物理量，电压其实是我们基于数学上面的操作所创造出来的一个虚拟的物理量啊。电流是真的，电压其实不是。电压其实是电场经过一个路径的作用之后所得到的效果。不过没关系啦，大家都用这么久了所以你当然还是可以继续用电压。至少它好用嘛，OK。Before proceeding further, we record that the voltage between 2 points A and B in a time-varying electrical field is in general dependent on the paths followed from A to B. In our previous discussion about generator or electric motor, we know that voltage difference between point A and point B can be different depending on the time variant behavior of background magnetic field. However, in the condition of static field, without the time variant part, the curl of E is what? It's a constant. It's a constant under the static field condition. If the magnetic field is time variant, the voltage difference or the potential difference between 2 points is a function of the path that you integrate. On the other hand, if the magnetic field is static, the field is static, it's not time variant, then the integration of electrical field intensity under different paths is the same. In other words, for steady electrical field, the electrical field is the so-called conservative field, pretty much the same as the gravity field. Gravity field is the so-called conservative field. Steady electrical field is also conservative field, which is independent of the integration path. So the work you need to perform from climbing from the first floor to the third floor is the same, no matter which step you are taking. 所以假如你是进场的话，你的那个电位差跟积分的路径无关只跟你起点跟终点的位置有关。这是我们对保守场的定义啦，保守场的定义。那再延伸一步讲的话，就是说对于保守场来讲的话，假如你的积分路径是一个封闭圈子if you perform a closed loop integral, then the voltage, the potential accumulated with this loop integral is what? Is zero for steady field. For conservative field, it shall equals to zero. If you move back to the point that you start, to the original point, then the potential difference is zero for steady field, right? Okay, so anyway, for steady field, you need to remember that the electrical field intensity equals to the negative of gradient of V. Why there is a negative sign here? Well, because 150 years ago when we defined the define the relationship between electrical field and the voltage, which says, oh, okay, the electrical field is pointing from high potential to low potential. And because of this definition, we need to put a negative sign here so that the mathematical operation is correct. 所以这是一个历史因素啦，因为我们当初100年前在定义电场方向的时候，我们是高电位指向低电位，事实上当初弄错了，因为低电位指向高电位的话，它就跟数学式是相符合的，所以结果就是我们有一个负号了，在我们讨论电压跟电场的关系式的时候，你多了一个负号。Alright, so let's move on to our next topic, the calculation of electrical scalar potential based on charge distribution. So in the following example, we will try to derive the expression for V, the electrical expression for electrical scalar potential. And to demonstrate, the purpose of this example is to demonstrate it's so easy. It's much easier to get E from distribution from function V instead of calculating E in terms of Q. 好，我要讲的是什么？我们接下来大家会看3个 example 了，所以这3个 example 的目的是要告诉你说，你假如先算 potential， 比如说 phi 或者是 A 的话，那么要去算它所对应的场，也就是 E 跟 H 的话，因为说从 Q 跟 J 来去算 phi 跟 A 比较容易，而以前我们在 Chapter 1、Chapter 2的时候，我们有用 Q 直接算 E， 或者直接用 J 来去算 H， 那个时候的计算比较麻烦，你要去用到一些积分微分的技巧，还有一些空间对称的关系，你才能够去解题。但是在这里你会发现，用那个用电荷分布或电流分布直接去算 V 去算 phi 跟 A 没有那么困难，那一旦你有了 phi 跟 A， 你只要做一次的空间偏微分，你就可以得到电场跟磁场。好，这个是接下来这几个 example 的目的。那 on the slide, you see that this is what? This is the field distribution established by a point charge. So again, we were starting from point charge. So we know that for a point charge, you will have outgoing electrical field directing away from the position of the electrical charge. Suppose that the electrical charge is positive, then the field built up by the charge is pointing outward. So the solid yellow line is the electrical field vector. However, based on the distribution of Low's electrical field, you can draw the dashed line, which is what? Which is the so-called equal potential lines or equal potential surfaces enclosing this point charge. If the point charge is positive, we know that it has this field, this circle has a higher electrical potential. This one has a slightly smaller one. This one, which is further away from the point source, has even smaller electrical potential. And if you have a point charge as drawn in this figure, you will have a spherical equal potential surfaces. All right? And we also know, based on the Coulomb's law, Coulomb 定律, the electrical field intensity due to a point charge, say Q, equals to what? Equals to Q divided by 4 pi epsilon times R to the square. So we know that The electrical field intensity is proportional to the charge density. Is inversely proportional to the distance from the source, R. And the direction of the electrical field is pointing away. So you have AR, that is the unit direction, unit vector pointing outward from the region. Okay? So that's what we already learned. Then, in this slide, we try to find out what? Find out the electrical scalar potential due to the presence of a point charge. Due to the presence of a point charge. So if we now consider two equal potential surfaces, say with radii as R and R plus dr, the potential drop from the surface of radius R to the surface of radius R plus dr is Q divided by 4 pi epsilon R to the square times the distance dr between the two surfaces. Or this is the incremental potential rise, dV. The amount of change in potential V can be expressed as this thing, the electrical field intensity, which has small distance dr. 所以这边你看到的是我们刚刚有电荷源所建立起来的电场嘛，那你把这个电场沿着特定的距离走一小段，也就是我们这边写的 dr。那这个电场乘向一小段的那个距离，得到的就是它的电位差，所以等号的左边写作 dV 嘛，也就是电位多了一点点，等于那个电场大小乘上一点点的路径长度，所以是不是这个东西其实就是我们那个前面写的那个嘛？所以中间那个式子其实就这个式子，这个东西呢可以看作是这整个东西都有一分，然后事实上你只是把这个式子去做一个积分，就相当于这个东西 ，OK， 那当然嘛，因为是积分的关系，所以你多出现了一个未知数叫 c， which is a constant， if you taking the integral of this thing, you end up with Q over 4 pi epsilon R plus C, in which you are at the liberty to determine what C is, as long as it's a reasonable guess, it's a reasonable assumption. 所以只要你的选择就是说这个 C 这个常数是可以你自选的，只要它的结果看起来合理就好了，And because of this integration operation, we end up with an expression for the voltage, the potential, V, which is a function of R. Why? What is the significance of this expression, V as a function of R? Well, because we have a point source, and the electrical field produced by this point source is symmetrical. Spherically symmetrical. So it's independent of theta and phi in the spherical coordinate system. It's only related to the distance r. So the expression for V can be reduced as a one-dimensional function. That is, it's only related to position r, the distance r. And it equals to Q over 4 pi epsilon r. 所以注意到我们在电路学学过嘛，电场强度跟距离平方成反比啊，电压大小嘞，跟你到 source 的那个距离的一次方成反比嘛 ，r 分之一的关系嘛，因为 V 是电场一积分之后的结果，所以它跟距离的那个关系会从 r 平方分之一变成是 r 分之一。然后当然我这边有个 c 的未知数不过你给他一个合理的答案就好了合理的猜测就可以了 So we can choose C such as that V is 0 at some arbitrary reference point, and intuitive guess is set the reference points to somewhere to the infinity. Says if the voltage reference is 0 for a very, very distant point, then C can be reduced to 0. Right? So by choosing this assumption, assuming that the voltage, the potential at a very far away place is 0, then the relationship between charge density, between the charge, amount of charge, and the voltage V is this, V equals to Q over 4 pi epsilon r. So we see that the voltage, the potential is inversely proportional to the distance r. So now we have the relationship between voltage, the potential V, and the point charge. So the next thing is to, and we already revealed that it's inversely proportional to R, while electrical field intensity E is inversely proportional to the R square. Now we are trying to find out the field distribution E for a more complicated charge distribution. 所以在下一页里头，我们要做的事情是要找到一个电场的表示式，电场分布的表示式。而这个电场分布的表示式事实上是由比较复杂的点电荷分布所组成的比较复杂的点电荷分布所组成的。那我想我们今天就停在这边好了啦因为这个我们剩下2分钟，你稍微讲一下Example 5.2 的话，描述的是一个所谓的电偶极 electrical dipole which contains 2 electrical point source of the same magnitude, and they can be regarded as the separation distance between the 2 charges is d, so that you can imagine that the 2 point sources are located on these 2 positions. That is along the aligned with the z-axis, and the distance of Q and minus Q is the same toward the origin. So you have so the positive charge Q is placed above the origin by half of d, and the negative Q minus Q is located under the negative z-axis by d over 2. And we would like to find out the electrical potential as well as the electrical field intensity expression for the electrical dipole. To the right is the solution. I don't know if you are acquainted with this kind of distribution. This is the, so let me see, okay. So this is, the borderline is the electrical field line, 电场线，比较粗的是电场线，然后那个绕一圈回来比较细的是等电位线。那因为它是正电荷配上负电荷嘛，我们称之为电偶极，所以电场线会从正电荷出发，然后结束在负电荷。那从这一个分布来看，你会觉得它其实有点复杂咯。它会牵扯到一些三角函数了虽然说它看起来也不是那么的乱了但是至少不是几条直线就可以表示得出来所以在这个 example 里头，我们就要展现说，用先算电位再算电场的方式，可以让你在不是那么费力的情况底下，得出一个电偶极的电场电位分布。OK， 好了，我们今天先到这里吧。OK， 好。